columns are broken up into several different categories. So first of all, we've got short versus slender. So a short and stocky column. Yes, question?
Did you finish the column at the end of the class last week?
You know, we didn't get into our crack control, and we'll pick up the crack control for slabs in the lab for the example we're doing there. Yeah, so we basically got to the point with our concrete slab that we kind of carried over in the lab and continued on there. Okay, so concrete columns, short and stocky, so no buckling. We're focusing just on the compressive resistance of the concrete alone. Now we do still put reinforcing even in a short and stocky column where there's no potential of lateral movement. We do have an earthquake requirement to do what's called confinement steel. So if we've got a column, we're going to have a couple of longitudinal bars, at least one in each corner as a minimum. If we start looking at columns in detail, we'll see sometimes we have 3 or 4 bars per side, depending on the configuration. But it's really this part right here where we're putting in a stirrup around those bars. Right? So those bars, just like we had with our shear reinforcing and beams, are going to be spaced out over the length of the column. Now the design requirement is a little bit different. This is not shear reinforcing, although it does provide some shear reinforcing when we get into the bending of the columns. But it's what we call confinement steel. So the idea here is that if we have a once-in-a-lifetime event like an earthquake, and the concrete is shaken back and forth repeatedly at fairly high displacements, what can happen is, we're drawing the longitudinal bars here, what can happen is big chunks of concrete will actually fall and fall right off. But what happens with the reinforcing that we have in here is it contains that inner chunk of concrete. It may still crack quite significantly and be damaged, and that confinement steel can bend and buckle and so on. But what it does is it keeps the inner core of the concrete relatively intact. And remember that the primary goal of a column is to resist those compressive loads. So even if things are kind of warped and distorted and heavily cracked and missing chunks, it can still take a compressive load as long as that steel is holding that inner core together. It might be rubble inside there, but it's still actually holding quite a significant amount of vertical load. Right? So the idea here is that during an earthquake, right, we may have significant damage, but at least the column is not going to collapse, and it'll still be able to hold the building up at least long enough for people to get out afterwards. Right? So we still will have reinforcing in, regardless of the kind of design that we have here. Now, in addition to short versus slender, we also have another classification of sway versus non-sway. And basically what that means is that the element is allowed to move sideways, right? So with a sway type column, the frame of which that column is part of takes the horizontal. And for non-sway, we would then have to have a separate shear resisting element. Now, we've been focusing in class on design of system for which we have a specific lateral load resisting system, brace frames, shear walls, and what have you. So from our perspective, we're not going to talk about non-sway. They're a little bit more or not talk about sway rather. They're a little bit more complex. So we're going to focus on the non-sway, and then we'll take a look at short versus slender. Now, in order to determine if it is non-sway, it's a fairly simple formula. So we have a parameter Q that we're going to calculate, and if this is less than 0.05, then we consider non-sway. And Q is the sum of PF delta divided by VF. That's the where our delta zero is lateral story deflection. Right, so again, we got some of the compressive loads, our PF. Our VF, of course, is our factored shear of the story, and LC is our length of our column. So those ones are fairly straightforward, but it's this lateral story deflection is the one that really causes the issue. We need to actually calculate for a building how much each story is going to laterally deflect. And if it deflects sufficiently, then as we go through this calculation, then our columns end up having to be designed for sway. So taking that displacement specifically into account, as well as the axial and bending that we have on there as well. So this involves a full analysis of the entire building. It's not just a matter of doing a calculation on an individual column and see how much it's going to deflect. I now need to put into S-frame. It's all statically indeterminate. It's all frame analysis. And so there's a lot of calculations involved there. So that's one of the reasons why we're not going to look at whether or not something is swayed or not. But the equation, once we get this delta zero, is actually relatively straightforward. Okay, so let's focus on our non-sway. Code reference. So we have this formula here, and what this formula is to determine whether or not our column is considered short and stocky or long and slender. So in other words, the way it's expressed is that slenderness effects can be ignored if we meet this requirement. So what we'll do is we'll calculate this quantity here, and we'll compare that to the KL over R for our column. And if we are less than that, then of course we can just design based on axial load only. And there's a straightforward table for looking at straight axial load. We'll look at that in a minute. If this number is bigger than this number, then what we've got is something which is considered long and slender. So now what we have to do is go through an additional calculation to basically amplify the moment effects. Now you'll notice in this equation here that we've got this ratio of M1 and M2. M1 and M2 are the two end moments on the column. M1 to M2. And this ratio is always less than 1. Now, when we're looking at concrete systems, what we typically have is our concrete column is part of a bigger system. Right? It's not that we have a column and then sitting on top of that is a beam and they are physically separated except for the fact that they're in contact like we would have with, say, wood structure. But I mean, even nowadays with wood, we're still putting pins and stuff in there to put in an uplift resistance. But with concrete, we actually have rebar that ties in between the concrete and the beam. Even though the concrete and the beam might be two separate concrete cores, the concrete is all tied together through that rebar. So that means we have moment transfer between the two. So when we're looking at our column, we never really have a situation with a concrete column that is a pin-pinned situation. When we were looking at steel and wood, we were often considering our columns just to be pin-pinned. This made the design actually fairly straightforward because now we were just dealing with axial load only. So here with concrete columns, for the most part, there's going to be some moment transfer. And the idea here is that if I've got a concrete column and it's connected to a concrete beam in here, then what happens is as I put in my load patterns, and again, our concrete beam is usually a statically indeterminate system. And so there we're analyzing that into S-frame, and we're putting in all these multiple load cases, skip live loading patterns, and so on. And what happens is, as this deflects under various load, this imparts a moment onto our column. Right? So this maintains this 90-degree connection in here. Right? So as our floor systems move under the different loading patterns, it causes this column to move out to the side, so therefore we actually have moment transfer between these two elements. Right? So we do have moment. Now, in order to analyze what these moments are, involves a frame analysis in S-frame. Now, there are some equations in the book. We saw those simplified formulas for beams and slabs, which allowed us to calculate moments and shears, right, both positive moment, negative moment for continuous systems. There are actually some tables that exist in a variety of different design aids that allow us to figure out frame loads as well. So analyze the entire frame and come up with some generic values. But by and large, these are usually handled by analyzing the entire frame within S-frame. So what we would be looking at is doing this sort of pattern within an S-frame. And then putting in fixed supports on here instead of pin supports. Right, and again, as we go through and analyze our loading patterns, we're putting in skip live loading patterns, which does that sort of thing. Right, so just like we do an alternating load pattern on a beam line, we do an alternating on per floor as well. Right, and this actually causes a worst case effect to have this alternating pattern going like this. And it's based on the influence lines that we were looking at for beams. They can be extended to frames in much the same kind of way. So from our perspective here, we're going to say, we're not going to get into the frame analysis side of things. Again, that's all S-frame related. So we're going to start with an M1 to M2 ratio. Now, depending on our configuration, we may end up with this number being positive or negative. Right, so positive for single curvature, and negative for double curvature. So really what we're looking at for single curvature, we're talking about that kind of behavior, popping out to the side as I go here. But if I had the other column here, let's say our floor system is doing this, in order to, so one floor is rotating this way and the other floor is also rotating the same way. In order to maintain your 90 degrees in here, right, we end up with this double curvature configuration. So there's curvature one way and curvature the other way. Right, so in that double curvature configuration, we would put in this ratio of M1 to M2 as negative. Now, technically, if I had triple curvature, it would be positive, and quadruple curvature would be negative, and so on and so on. So mathematically, that's how it works out. But in practice, we don't normally ever see anything more than a single curvature, double curvature in our concrete frames. Now, this ratio of M1 to M2 is not less than minus 0.5. If you calculate this ratio of M1 to M2, and we've got double curvature, so it comes out as negative, and it calculates out to less than minus 0.5, then we use M1, M2 equal to minus 0.5. It's not like the system does not work, right? So if M1 over M2 is less than minus 0.5, use M1 over M2 equal to minus 0.5. Now we also have a limit on our KL over R here as well. Right, so we see, so that's the M1 over M2 part in here. And on the denominator, we've got square root of PF over F prime C and AG. So PF is just our factored axial load on our column, F prime C for our concrete, and AG is gross area, so just based on the size of the column. So that part's relatively straightforward. So let's look at the KL over R part.
Gross area cross-sectional or?
Cross-sectional, yeah. Right, so if it's a 300 by 300 column, it's 300 by 300 in square millimeters. So K L over R has to be less than 100. And this is coming from 10.13.2. Now, we're going through a process here that's called the simplified analysis. And this KL over R less than 100 is related to that simplified analysis. It is technically possible to design a much more standard column where your KL over R is greater than 100, but now we're getting outside of the simplified analysis, so there's more calculations involved. Now, as part of the simplified analysis, what we can do is make an assumption here on R. So this is part of the simplified analysis. And this actually helps us quite a bit. Because if you remember the process that we're going through with steel, that as long as everything was buckling about the Y direction, I could just refer to the green pages and pull off the section size, and things work quite well. But once the X direction buckling governs, then we ran into a little bit more of a problem, because the tables were based on weak axis buckling, not strong axis buckling. So we had to calculate KL over R and use the CR over A table. But how do you calculate KL over R if you haven't designed the column and don't know which R value to use? Right, so you basically have to guess a size. And in our analysis, what we did is we guessed the size by assuming weak direction buckling, used that in order to guess the size, and then we checked the X direction to see if it worked. And remember that within section 6 of the back of the steel handbook, the columns are grouped by sizes that have approximately the same R value, which means if I need to adjust my R value because my guess isn't adequate, I can move within those groupings and not have to worry about recalculating KL over R, because that number essentially has to change. So as we look to concrete here, basically the same process applies. We can't calculate KL over R until we have a column size, and I can't get a column size until I actually go through this design. So having this little approximation here, where I can come up with the physical size of the column, so this is the cross-sectional area, and not worry about reinforcing just yet. It allows me to calculate a value for R, which I can then go through in here and determine whether or not we have some slenderness issues to take into account. Now, so that really does simplify the process quite a bit, being able to simplify it. So we're going to use 0.3H for rectangular columns, or 0.25H for circular. For the most part, there's not that much difference between rectangular columns and circular columns, although calculations for moment of inertia are a little bit different for circular columns. We'll talk a little bit about that as we get going. But we're going to focus on rectangular columns. In fact, for the most part, we're going to focus on square columns. Now, if our calculation for our KL over R means that we end up calculating a short column, then what we're going to calculate here is a column that has both an axial resistance as well as a moment resistance. In fact, we'll do the same thing for slender as well, but slight little difference. So for short columns, we're going to design for our maximum axial force, our PF, and M2. Now, M2 is a factored value, and again, if we're looking at this ratio of M1 to M2, this ratio is always less than 1, so that means M2 is the larger value. I'll specify that right there. Also, in terms of our sign, while technically the way the code is written is that this ratio M1 to M2 is either positive or negative. In practice, what that means is that we will consider M1 to contain the sign. Right? So we'll leave M2 always as a positive value. Not that it really makes that much difference, but it's a convenient way of thinking about it. Now, if we have slender columns, we're also going to design for axial moments, or axial end moment, but now we're going to take into account P delta effects. So this is 10.15.3.1. Now you remember with our steel columns, as we were taking P delta into account, there was a U2 value that we calculated. Right? U2 was that amplification factor which allowed us to take our design moment and then just magnify it. And in fact, technically we were considering just the component of moment that was due to lateral load. We have a similar process here. It's not a U2 value. We have an MC that we're going to be looking at. So MC is our amplified moment. So like for short columns, we designed for PF and M2. Here what we're going to do is design for our PF and MC. Right, so MC is that amplified moment. And we have a formula to run through to calculate MC as well. So our formula for MC involves a little Cm times our M2. Again, we're taking our larger moment M2 and multiplying, or scaling it up basically. So Cm times M2 divided by 1 minus Pf divided by phi m and Pc. Cm is 0.6 plus 0.4 times M1 over M2. And this number has to be greater than or equal to 0.4. This calculation for Cm, at least this formula here, assumes no transverse loads. You remember as well when we were looking at our steel columns that there are some modifications to the formula in the omega-1 term that take into account different loading patterns, right? And we just use the omega-1 term equal to 1 divided by the rest of the formula for our standard configuration. This is our standard configuration where the moments are applied by transfer from the floor system, not due to any horizontal loads within the beam or within the column itself. If there are horizontal loads in the column itself, then we have a different formula. So again, we're not going to focus on that one. We're going to stick on our basic standard formula here. If we do have transverse loads, Cm, it's actually just 1. Or Cm equal 1. Right, so this formula here is 10.15.3.2, and this one 10.15.3.3. Now you'll notice as well in this formula that we say that this term here has to be bigger than M2. Obviously this is a scaling up factor, right? So it is possible under some circumstances that this will give you a number less than M2, right? So we're not going to allow this process to reduce the overall load. Right, so that has to be bigger than M2. So if this ends up being less than M2, then we're just going to use M2 directly in our calculations. Now I should also point out here as well that we have a difference between how certain parameters are expressed within the code. When we take a look at our KL over R, we say our KL over R has to be less than 100. Right? This is in order to use our simplified analysis. What that means is if I calculate a KL over R and it's more than 100, what we say is it doesn't work. And the only way to continue is to make the column bigger. Right? Increase the size so that R changes so that our KL over R will end up being less than 100. So we increase the column size. It does not work if the KL over R is greater than 100. Whereas for our ratio of M1 over M2, where we have to be less than minus 0.5, or this one here, where this has to be greater than 0.4, what it means is if I calculate that value out, and it is greater than 0.4, then I'm going to use CM equal to 0.4 in the calculation. It's not I've got to stop and redesign it. Right? So there are two different kind of parameters, different types of parameters that we see in there. Right? So so it's only this KL over R less than 100 that if it happened to exceed it, you have to stop and redesign and start from scratch. If anything else, we're just taking that as a limit. Okay, there is also a little note on M2. M2 has to be greater than or equal to PF times 15 plus 0.03H. And this is 115.1. Usually this is the case at M2. So this is M2 as it relates to this calculation. So taking our maximum axial load and multiplying by some eccentricity. Remember that in the steel code, the effect that we used to take this into account was basically the notional load. Right? So the idea behind the notional load, remember in steel, was that we're taking 0.2% of the weight of the building and applying that as a horizontal load at each floor of the building. To take into account the columns might not be perfectly plumb, the loads might not necessarily be centered within the columns, and so on. So there's a certain amount of eccentricity, right? A minimum eccentricity or lateral load that was taking it into account. Here, this parameter basically does the same thing. That we're saying, regardless of what your frame analysis was and what you calculated as your moment, we're going to take our moment to be at least as big as some minimum value. So that even if I calculate that there is no moment on our system, we're still going to end up applying a moment anyway, and ending up having to design our column for a little bit bending. Yes?
Does that also apply when we're doing short columns?
Yes, that's right. Yeah, so that's right. So we're looking at when we're designing here for M2 here. There's a certain minimum. That's right. So M2 and then MC where this is built up with M2. Now this does not affect that M1 to M2 ratio. Right. So when I say that this M2 here affects what we have in this calculation or what we use in here, right? Our M1 to M2 ratio. Right, we have a calculated value, and we're going to use that calculated value regardless of what we end up with here for my M2. Right, so I don't want this calculation to override that ratio.
So that 15 plus 0.03H, that's all in meters, right?
Yes, that's right. So that's right. So we're looking at well, I mean, yeah.
Because the height would be in meters.
The height is in meters, so that means this has units of meters associated with it as well. So yeah, so this is kilonewtons and meters coming up with kilonewton meters, basically.